Hello, my name is Mark, and in this video I want to talk about pi number computation that I am doing on Intel 8080 CPU. I am doing that by using my designed Intel 8080 single board computer, and all code would be written on C by using the 88DK toolchain. So let's get started. There is variety of algorithms to compute pi, but for the start I have chosen Spigot algorithm. It's very basic and simple, and I already implemented it before, so it shouldn't be a big deal to do that. Algorithm uses such formula for pi, and in such formula we can notice that pi is just infinite amount of 2's. But in some complicated mixed radix base C. So our goal is just to convert pi in that base into decimal form, and that's it. Basic implementation, as I mentioned, is quite simple and straightforward. In minified and obfuscate form, source code is just less than 200 characters. But of course my code is a bit bigger, but still could fit into a single screen. I compiled the code and ran it on real hardware, and just after 40 hours I got correct result. Of course 40 hours is not a great time, so that's why I started to think about another algorithms that I can use, and of course first algorithm that popped into my mind is Chudnovsky algorithm. This algorithm has been used for past several records for pi digits computation. Recently Linus Tech Tips used Y-Cruncher, which implements that algorithm, to retrieve 300 of trillions of digits of pi. Okay. How this algorithm works then? We have such a Chudnovsky formula of pi number, and after a couple of transformations we can simplify it in such form that we have a and b as two infinite series, and we iterate through k until we don't reach necessary precision. Code to implement such algorithm is also very straightforward. We just compute some coefficients, numeric coefficients, and then have a loop to compute a and b. And after that just perform a simple division and got our pi number. We don't need to implement proper float arithmetics. We need just to store numbers with some scaling factor. N's power of 10, where is n our desired amount of digits plus some extra number to achieve necessary precision. Even in such simple program I had couple of tricks. First trick is to pre-allocate all variables in memory, because Intel 8080 has limited amount of space, it's just 46 kilobytes of memory. Another trick, I already mentioned that, was to extract computation of all coefficients outside of the loop. So you just compute them once and reuse inside loop when necessary. And last trick that worth to mention is to skip implementation of signed numbers. You can just track sign of a couple of variables separately and don't implement proper signed arithmetic. First run to compute 1000 digits of pi took around 12 hours. It's probably still better than Spigot algorithm, but I have a lot of places to improve. In my first naive version I have used the BCD storage format for numbers. It means that 1 byte held just a single decimal digit, which is not very efficient. So first thing that I wanted to change is to change that storage format to base 256. It means that I would use whole byte to store digits, and numbers would take less memory. and it means that we would have shorter loops and we don't need to carry by ourselves. But to my surprise, I got quite poor results. Same program with only that change now took 23 hours to execute instead of 12 hours, so twice as slow. Why? I produced flame graph and studied that and found out that I have operation to multiply by number that is power of 10, which is very fast when you use BCD storage format. You just can shift bytes, copy bytes from one location to another. But for my changed storage format, I perform actual multiplication, which is slow for big numbers. I have to multiply by number which is power of 10 because of my decimal fixed point. So I mentioned that I have chosen a scaling factor as nth power of 10. But what if we choose some binary decimal point, binary scaling factor? It should help. But now we can't convert our numbers into decimal form quite easy. We need to perform additional computation. But fortunately enough, this computation is not that heavy. We just need a loop to multiply a number by a single 10 several times. And it would be enough to extract decimal digits from that final number. After the change, I got much better time, just 2 hours, which is good. It's better than 23 hours or even 12 hours for initial version. But I wanted to compute 10,000 of digits of pi, not just 1,000 of digits of pi. And after simple approximation, I estimated time that would require to perform such task as about a week or so. So it's still not good enough. I took another flame graph, and it's obvious that multiplication is slow. What can we do with that? Usually I start to write the most trivial code and then improve it, because premature optimization is the root of many evils. I did it in that case as well. I implemented simple and straightforward pencil and paper multiplication from school. But this method could be improved. I used algorithm from a handbook of applied cryptography, just some small rearrangements, and this change allowed me to gain 100% of performance improvement. Great! So now let's take another look of new flame graph, and you can notice that right now 80% of execution time is done to compute square root. I knew about algorithm of fast integer square root that could be used in low performance microcontrollers. But after I implemented that, there were no change in time. So I started to look into another places. Division is quite frequent operation that is used by square root calculation. So I started to think about more performant algorithm for division instead of algorithm D from Kmut that I have used originally. And I thought about divide and conquer recursive division. It has own limitations, but in my case usually it's faster than original implementation. You can notice that this function is a recursive function. So how it would work with our manual variable allocation in memory? I had to juggle with pointers and use only input operands, so I would modify them in place in nested calls. It required from me to rewrite a few functions, but that's okay. Even if it was not main optimization, it still cut another 10 minutes from target time, from computation time. What have I meant that it's not main optimization? Yes, it cuts 10 minutes, but it would be much beneficial in conjunction with another divide and conquer algorithm, Karatsuba multiplication. Because in original school book method of division, multiplication is performed for some large number multiplied by a single digit. So we can't receive big benefits by using Karatsuba multiplication. But now, after we changed division into divide and conquer algorithm, we can implement Karatsuba multiplication and it would be great. I'm not going to talk about Karatsuba multiplication. There is already a lot of videos and articles about that algorithm. Just want to mention that it's beneficial because it replaces one multiplication by a couple of addition, and usually it is faster. That improvement allowed me to achieve 30 minutes mark. But divide and conquer division algorithm and divide and conquer multiplication algorithm has some overhead for small numbers. So usually these algorithms are applied after some thresholds, so it applied only for numbers with big amount of digits, and it could be different thresholds. So I wanted to measure that thresholds for my hardware, and I performed a few tests. Here is heat map of thresholds, and looks obvious what values we want to use. But if we change our scale to zero-based, it's less obvious. So it looks like there is no much difference between thresholds. So I just picked lowest one. 30 minutes is good, but I still thought that it could be some better algorithm for square root itself. So I continued to dig around and finally found out what algorithm is used by GMP, and it's a similar divide and conquer principle. Here is algorithm, and after implementing that I gain another 200% of improvement. 10 minutes is good enough for me, so I stopped on that point. Here you can see a table of optimization that I have performed and time that I got after such optimizations. And final number is 60 times less than initial BCD implementation. So I am happy with that. Now it's time for my original goal, 10,000 digits of pi. And the program finished in less than a day, 16 hours if I want to be precise. It is not first time when I compute digits of pi on some old Intel CPUs. So I gathered all data into a single table. Data looks reasonable. Maybe one interesting detail is that difference between Intel 80008 and Intel 8080 by using same algorithm Spigot and same digits of pi, 2048. Difference in time just 100%. So Intel 8080 just twice faster than Intel 80008. As usual, I published source code of all programs in my GitHub, so you can check it. Anyway, thank you for your time and hope that this video was a bit interesting for someone. Bye bye.